yes, an overcurrent protection device is required. The National Electrical Code, specifically Article 220, mandates overcurrent protection for conductors supplying a motor or other load that could create an overcurrent situation. In this scenario, the generator feeds a 480-volt switchgear and a fault could lead to an overcurrent. An overcurrent protection device installed between the generator and the switchgear safeguards the conductors from potential harm. This protection can be realized through a circuit breaker or a fuse. The appropriate size of the overcurrent protection device hinges on the ampacity of the conductors involved and the maximum overcurrent the conductors might experience. Understanding conductor ampacity is paramount. Ampacity refers to the current carrying capacity of a conductor, the maximum current, in amps, a conductor can carry continuously without exceeding its temperature rating. Factors influencing ampacity include the conductor material, its size or gauge, insulation type, and the ambient temperature. The NEC provides tables, such as Table 310.15b16, which offer ampacity ratings for various conductors based on these factors. When selecting an overcurrent protection device, you must ensure its rating does not exceed the conductor's ampacity. This prevents the conductor from overheating and potentially causing a fire. Several considerations go into selecting the right overcurrent protection device. Firstly, consider the type of load. Different loads have varying inrush currents. For example, motors typically draw a high inrush current during startup. The overcurrent protection device must be able to handle this inrush current without tripping unnecessarily. Secondly, consider the available fault current. This is the maximum current that could flow during a short circuit. The overcurrent protection device must have a sufficient interrupting rating to safely interrupt this fault current. Thirdly, consider the coordination of overcurrent protection devices. In a system with multiple overcurrent protection devices, they should be coordinated so that the device closest to the fault trips first. This minimizes the extent of the outage. There are two primary types of overcurrent protection devices: fuses and circuit breakers. Fuses are one-time devices that melt and interrupt the circuit when an overcurrent occurs. They are relatively inexpensive and offer excellent current-limiting capabilities. Circuit breakers, on the other hand, are reusable devices that trip and interrupt the circuit when an overcurrent occurs. They can be reset after the fault is cleared. Circuit breakers are more expensive than fuses but offer greater convenience. When installing an overcurrent protection device, it is important to follow the manufacturer's instructions and all applicable codes and standards. The device should be installed in a readily accessible location and properly labeled. Regular inspection and testing of overcurrent protection devices are essential to ensure they are functioning properly. This includes visual inspection to check for any signs of damage and testing to verify the tripping characteristics. The NEC provides specific requirements for the installation and testing of overcurrent protection devices. In the context of a 1000 kilowatt generator supplying a 480 volt switchgear, specific calculations are necessary to determine the appropriate overcurrent protection. The generator's full load current must be calculated. This involves converting the kilowatt rating to kilovolt amps, considering the generator's power factor, and then using the voltage to calculate the current. For example, assuming a power factor of 0.8, the kilovolt amps would be 1000 kilowatts divided by 0.8, resulting in 1250 kilovolt amps. The full load current would then be 1250 kilovolt amps multiplied by 1000, divided by the voltage 480 volts, and divided by the square root of 3 for a three-phase system. This calculation yields approximately 1804 amps. The generator's overcurrent protection should be sized no more than 125% of the generator's full load current, unless otherwise permitted by the NEC. In this case, 125% of 1804 amps is 2255 amps. A standard size circuit breaker or fuse should be selected that is closest to, but not exceeding, this value. The busway connecting the generator to the switchgear also needs to be considered. The busway must have an ampacity rating equal to or greater than the generator's full load current. The overcurrent protection device will protect the busway in the event of a fault. It is important to coordinate the overcurrent protection device with any other overcurrent protection devices in the system. This ensures that the device closest to the fault trips first, minimizing the impact of the fault. Coordination studies are often performed to determine the appropriate settings for overcurrent protection devices. Additionally, consider the generator's short circuit contribution. The generator will contribute to the fault current during a short circuit. This contribution must be taken into account when selecting the interrupting rating of the overcurrent protection device. The interrupting rating must be high enough to safely interrupt the maximum fault current. Article 445 of the NEC provides specific requirements for generators, including overcurrent protection. It is important to consult this article to ensure compliance. Furthermore, Article 700 of the NEC addresses emergency systems, and Article 701 covers legally required standby systems. If the generator is part of an emergency or standby system, these articles may impose additional requirements. In summary, installing an overcurrent protection device between the generator and the switchgear is essential for protecting conductors and equipment from damage in the event of a fault. The selection and installation of the overcurrent protection device must comply with all applicable codes and standards, including the National Electrical Code. Careful consideration must be given to conductor ampacity, load characteristics, available fault current, and coordination of overcurrent protection devices. Regular inspection and testing are also essential to ensure proper operation. The specific calculations and requirements will depend on the generator's size, voltage, and application. Consulting with a qualified electrical engineer is recommended to ensure that the overcurrent protection system is properly designed and installed. The 30-foot busway plays a crucial role in this setup. The busway acts as the conductor connecting the generator to the switchgear. Therefore, it must be adequately sized to handle the generator's full load current, as determined by the calculations mentioned earlier. The busway's ampacity rating must equal or exceed the calculated full load current of approximately 1804 amps in the previous example. Exceeding the busway's ampacity rating can lead to overheating and potential failure, creating a fire hazard. The busway's construction and installation must also adhere to NEC standards. This includes proper support, insulation, and clearances from other equipment and materials. The NEC provides tables and guidelines for determining the appropriate busway size and installation practices based on its ampacity, voltage, and environmental conditions. Grounding is another critical aspect. The busway must be properly grounded to provide a low impedance path for fault currents. This helps to quickly trip the overcurrent protection device in the event of a ground fault, minimizing the risk of electric shock and equipment damage. The grounding conductor should be sized according to NEC Table 250.122, which bases the conductor size on the rating of the overcurrent protection device protecting the circuit. The overcurrent protection device protecting the busway also protects the generator. In the event of a short circuit or overload on the load side of the switchgear, the overcurrent protection device will trip, disconnecting the generator from the fault. This prevents the generator from being damaged by the excessive current. The location of the overcurrent protection device is also important. Ideally, it should be located as close as possible to the generator's output terminals. This minimizes the length of unprotected conductor between the generator and the overcurrent protection device. However, practical considerations, such as space constraints and accessibility, may influence the device's final placement. The NEC provides guidelines for the maximum length of unprotected conductors in various situations. Coordination between the generator protection and the switchgear protection is crucial. The overcurrent protection device protecting the generator should be coordinated with the overcurrent protection devices in the switchgear to ensure selective tripping. Selective tripping means that the overcurrent protection device closest to the fault should trip first, minimizing the extent of the outage. Coordination studies are typically performed to determine the appropriate settings for the overcurrent protection devices to achieve selective tripping. These studies involve analyzing the fault currents at various points in the system and selecting the overcurrent protection device settings to ensure that the devices trip in the correct sequence. The generator manufacturer typically provides recommended overcurrent protection settings for the generator. These recommendations should be considered when selecting and setting the overcurrent protection device. In addition to overcurrent protection, the generator may also require other types of protection, such as undervoltage protection, overvoltage protection, and reverse power protection. These protections are typically provided by the generator's control system. Undervoltage protection protects the generator from damage caused by low voltage conditions. Overvoltage protection protects the generator from damage caused by high voltage conditions. Reverse power protection protects the generator from damage caused by motoring. Motoring occurs when the generator is driven by the load instead of driving the load. This can happen if the prime mover fails or if the generator is connected to a system that is already energized. The generator's control system should be regularly tested to ensure that all of these protections are functioning properly. The testing should be performed according to the manufacturer's recommendations and applicable codes and standards. Proper maintenance of the generator and its associated equipment is essential for reliable operation. This includes regular inspection, cleaning, and testing. The maintenance schedule should be based on the manufacturer's recommendations and the operating conditions. Keeping detailed records of all maintenance activities is also important. These records can be used to track the performance of the generator and identify potential problems before they become serious. In conclusion, installing and maintaining appropriate overcurrent protection for a generator supplying a switchgear is crucial for ensuring the safety and reliability of the electrical system. This involves careful consideration of various factors, including conductor ampacity, load characteristics, available fault current, coordination of overcurrent protection devices, and applicable codes and standards. Consulting with qualified electrical professionals is essential to ensure that the overcurrent protection system is properly designed, installed, and maintained.